Okay. Welcome to lecture 10. So today basically we're talking about deep learning. Okay. So I think this is the last lecture that we'll have. Okay. So next week, I'll talk a little bit about more advanced topic, and then we will have a quiz. Okay. So remember that the homework is due this week. Okay. I think it's still at the end of this month, and next week we'll have a quiz. So basically, it will be a closed book quiz, so that the question can be easier. So you can just bring a calculator. Okay, so the quiz will be 80 minutes. Okay, so it's closed book, so you don't need to bring bring a laptop. Okay, so it's closed book, so it's easier. If it's open book, then I have to make it more difficult than ChatGPT can answer. So closed book is actually easier. The question will be similar to the homework. Okay. Okay. So I think this week is week 10. So week 11 we'll have the quiz. Okay. So starting from week 12 and 13, so this will be the presentation. Okay. So I think you still don't have the detail of the presentation information, right? But next week I'll give you more detail. But basically, you just use like 5 minutes to make a very quick presentation of how the machine learning and AI statistics are related to your own research. Okay. Okay, so then let's move to the neural network part or deep learning. So how many of you have already used deep learning or neural network in your research or in your study? Please raise your hand. So what type of package are you using? PyTorch? Yes, please. Okay, some idea. Anyone who already wrote train a neural network before? Please raise your hand. Just let me know how many. I think definitely some of you definitely did this, right, in the past. Okay, so maybe I just go through the lecture first. I try to give you more detail of how it's implemented. Okay, so this lecture has already been used in another subject called urban big data. Big data. I'm not sure if you took that already. Okay, but I think I'll talk something that is different, a little bit different. Okay, so in the past weeks we learned several machine learning method. We talk about linear regression, logistic regression, and we talk about the perceptron. Okay, so actually there is a unified framework for this different method. Okay, say for example, linear regression, you can think of it as this is x1, x2, x3, and those are connected with W1, W2, and W3, and then you have a sum, and then you have the output. Okay, so you can see that when we talk about linear regression, it's actually y equals W1 x1 plus W2 x2 plus W3 x3. So you can actually write it like something like this. This is linear regression. Of course, sometimes you have a bias alpha, and then you just put alpha here. Okay. So this is linear regression. And what is logistic regression? Logistic regression just has one thing different. That is this output, you have to apply a logic function as a link function, and then you take the output. This gives you the logistic regression. Okay. So what is perceptron? We learned this last week. So it's also W1, X1, W2, X2, W3, X3, and your sum, and then you input it into a step function. Okay, so the step function will give you the output to be either 0 or 1. Okay, so step function basically says is greater than 0 is 1, if smaller and equal to 0 is 0. Okay, so you can see that actually we have a unified representation of all these three models. That is, you just have x1, x2, x3, all the way to xd, and then you have some connection, which is w1, w2, w3, all the way to wd. And for this, you do a summation and together with a bias, and then you apply a function, and then you output. And then you output. Okay, so basically here, you can see that here I have a function. This function can be, if it's a identical function. So if fx equals x, it's linear regression. Okay, if fx equals logit x, then this is logit regression. If fx is a step function, then it's perceptual. Okay, so you can see that we actually have a very universal framework that can coherently integrate linear regression, logistic regression, and perceptron within the same framework. Okay, and this framework, basically what we are doing is that given different inputs, we first apply a weight and sum them together. Okay, and then we apply a function. Okay, so we call this function in the neural network. It has a universal name. This is called a activation function. Okay. So basically, you just use W, multiply, and activation, and that's it. Okay. So that's something I'll show you. So you can see that no matter it's perceptual or linear regression or logistic regression, so basically we want to mimic a pattern like this. So this is actually very similar to a cell in your brain. Okay, so for example, for this cell, it has many connectivity, and different connectivity has different strengths, and this strength is modeled by the weight. And then you sum them together, you can determine whether this neuron is activated or not. Okay, those we call it activation function. Then we have some output. Okay, so that actually gives you the very basic unit in the neural network. Okay, so we call it a neuron. Okay, we call it a neuron, 神经元. Okay, so basically, we have, so for this neuron, there are some terminology. I just want to show you this terminology. So you can see here, for this neuron, you have, so basically you have two steps. The first step is that you calculate the summation. So here you can see that I'm using AX to talk about the summation. So the summation is bias plus the weighted sum. Okay, so the weighted sum, the W, you can write it as a vector. And then W times X can write like this. Okay, so you have B plus W transpose X. Okay, so this, we call it a pre-activation. The summation is actually a so basically it's something you have here. This is pre-activation. And then you will apply a function G here. So after apply the function G, then you have the output. Okay, so this output after the activation, we call it a output. Okay, so when we talk about a neuron, it always include a summation and a activation. Okay, so here the activation function is G. It can be a lot. Okay, so I just use a general term G. So you can see here, given for the HX is basically you apply this G function to the AX, and AX is here. You just plug in. Okay, very straightforward. And if you look at the notation, if you look at the figure, so it's very straightforward that you have X, And X is a d-dimensional vector. As we just mentioned, the feature dimension should be d, right? So you have a X dimension vector. Sorry, d-dimensional vector, and also the weight is also d-dimension. Okay, so d-dimension times d-dimension. This is a matrix. This is a vector multiplication. So you have a scalar. Okay, a scalar times a scalar is also a scalar. So here you can see that pre-activation is a scalar, and after activation is also a scalar. So here ax is a scalar. Okay. Okay. So when we do neural network, the most important thing in the neural network is understand the dimension. Okay. So most of the operation in neural network is all about how you calculate the how you understand the dimension. Okay, so you need to be very sensitive on whether this number is a vector or it's a matrix or it's a tensor or it's a scalar. Okay, so this goes all the way through the whole process. Okay, so now we have the name. We call W weights. Okay, we call W weights, and we call B bias. Okay, and then we call G activation function. Okay, and W and B together, we call it parameter. So for this neuron, you can see that W and B are what we don't know. So the activation function does not have parameters. Activation function, most of the time, it does not have parameters. Okay, it's just a function. Okay, so here as a neuron, so what thing had changed, a neuron will change. So you can see that if you change different W and B, this neuron will change. Okay. So let me give you several activation function as an example. I just mentioned if it's Gx equals X, so we call it a linear activation. So basically this is no activation. Okay, so you just pass through. Okay, so this gives you linear regression. Right, so if you just use linear activation, you get the linear regression. So here you can see that there is no non-linear transformation. So this is a linear transformation, and there's no input squashing. Input squashing means that no matter what is your input, your output is the same. Okay, so this one, most of the time we won't use it in neural network. Okay, so I just want to know that this exists, but it's not very commonly used. Okay, so this one, I think you already see it. This is the logit. Okay, so in neural network, it has another name. It is called sigmoid. Okay, sigmoid activation function, short as sigmoid. Okay, so this is basically logit. Okay, and if you check the equation, it's the same. Okay, so what's the benefit? So you can see that this one is, first thing, it's nonlinear. Okay, so it's nonlinear, and it's squashing the input. So the output is always in 0 and 1. Okay, so the output is always in 0 and 1, and it's always positive. So and it's bounded, and also it's increasing, strictly increasing. So sigmoid is quite commonly used in neural network. So this is a commonly used one. Okay, so it's a good activation function. Okay, another one called tangent H. So short as tangent H, but the full name is actually called hyperbolic tangent. Okay, so the equation is very tricky, but it's okay. You don't need to memorize the equation, but eventually you can see that the final output is something like this. So no matter what is your input, it will squash the output from -1 to +1. So this is a little bit different from the sigmoid. Sigmoid is 0 to 1. This one is -1 to 1. And also its bounded is strictly increasing, it's nonlinear. Okay, so in many cases, the tangent H and the sigmoid can be used interchangeably. So these two quite similar, quite similar. Okay, so there's another one. This one is actually commonly used, very widely used in modern neural network, which is called ReLU, rectified in linear. Okay, so this one is very simple. It just takes the maximum of 0 and A. So the output is something like this. You can see that if it's positive, then it's linear. If it's negative, then it's 0. Very simple. Okay, so it's only bounded below, and it's, you can see this is still increasing. I shouldn't say it's strictly increasing. It's increasing, monotone increasing, but it's not strictly increasing. Okay, and this is nonlinear. Okay, so this is nonlinear. Okay, so ReLU is a very recent, I think recent 20 years, people developed this new activation function. It's very, it's pretty useful, very powerful. So in the past, when people talking about the neural network, the first one they developed is this sigmoid. Okay. Okay, so maybe I see a few things more. So I think you know that the neural network, later, if you train a neural network, you are going to calculate the gradient, right? You need to calculate the derivative of this activation function, because later you need to do gradient descent, back propagation. Okay, so what is a disadvantage of sigmoid or tangent H? So there is a very tricky issue for the sigmoid and tangent H, is that for this area, you can see that this is actually it can be from negative infinite to positive infinite. The input can be any number, but if you look at this area, okay, this is almost a flat line. Okay, and also you can calculate the gradient. You'll find this part, the gradient almost equal to 0. Okay, so the 0 gradient gives you a lot of issue. The most important issue is the gradient vanishing. Gradient vanishing means that because of the chain rule, for example, let's say we have y equals a, b, c, x. Okay, we calculate partial y, partial x. This equals to partial y, partial a, partial a, partial b, partial b, partial c, and partial c, partial x. Chain rule, right? Yes. So I think this is easy to understand. Okay. So what happens? For example, you use a chain rule, but in the middle, what happens if this one gradient equals to 0? If you find in the middle something equals to 0, then you can see that this whole gradient becomes 0. Okay, we call this a gradient vanishing. This happens a lot in a neural network with a multiple layers. Okay, so there's another issue which happens here. So if you calculate the gradient here, if I remember correctly, the gradient is greater than 1. Okay, so at the very beginning, so the highest gradient is higher than 1. So if every time the gradient is greater than 1, then you can see that this gradient is it will grow very quickly. It becomes a super large number. Okay, this we call it a gradient explosion. Okay, so both can happen depending on the activation status of your neural network. Okay, so both things are not good. Okay, no matter it's gradient vanishing or gradient explosion, it will harm your neural network training. So later when we talk about back propagation, I think you have a better understanding. But here you can see that no matter gradient is too small, it's not good. Gradient too large, it's also not good. Okay, then why the ReLU is a good one? So what ReLU, there is still gradient vanishing. Okay, Gradient vanishing still happens, but there is no gradient explosion. This one may still happen, but a gradient explosion will never happen because the maximum gradient for the red loop is 1. Okay, so no matter how many 1 you multiply together, it's still 1. Okay, so here you can see that red loop has this benefit that others don't have. So you can clearly see this here, the gradient greater than 1, which is not a good thing. So there are actually a bunch of activation functions. There are so many activation functions that I cannot enumerate. I think there's in Wikipedia, there's a list. Okay, so if you're interested, if you are doing deep learning, so at least you should be you should know some of them. Okay. There is a bunch. Okay, so here you can see there's a table. We mentioned identity. Okay, so binary step, this is used in perceptron, right? Logistic sigmoid, so I just mentioned the sigmoid, and tangent H, we just mentioned. So SMHT, I haven't heard about this, but yeah, and soft sign, sometimes you will see some particular neural network using this particular activation function. Okay, and we talk about the ReLU, and I think you notice that there is an issue of gradient vanishing in ReLU. So later you can see that people develop some others. For example, this Gaussian error linear unit. If you look at the curve, you can see that this part is no longer 0. Okay, so it may be better. And soft plus, this one is also, you can see that. So there's one more. This is also looks like a ReLU, but this part has been modified. Okay, and I think there's a commonly used one, this leaky ReLU. Leaky ReLU says that if it's positive, it's x. If it's negative, it's 0.01x. Okay, so there is still a little bit gradient here, so that it can avoid the gradient vanishing a little bit. Or there are even some parametric ReLU. Okay, so people sometimes use this, but you can say that ReLU is a milestone. After ReLU, people find that ReLU is pretty useful, and then you can see that the others looks very similar to ReLU, but they want to modify a little bit. Okay, so before ReLU, it's more like sigmoid. Okay, so there are so many, so I cannot enumerate, but basically the idea is that, so here, there is one very important criteria, is that this activation function has to be linear. Okay, so this is a requirement. It has to be linear. It has to be nonlinear. Okay. Okay, so what we are doing given a neuron, for example, if you are using neuron to do a classification, binary classification, basically, if you are using the sigmoid, basically we are doing a logistic regression, right? So we are doing a logistic regression, so you can see that something like here. So for example, our input is 2-dimension, and then here we are using the sigmoid as logistic. So basically, this is a 2-dimensional like logistic regression, okay? And your decision boundary is definitely something like this, okay? So basically, there will be a straight line cut this whole plane to two parts. One part is 0, another part is 1. Okay, so maybe this straight line is here, maybe this straight line is here, but basically we call this a linear boundary. So your decision boundary, the decision boundary basically means that on the both sides of this decision boundary is 0 and 1. Okay, so if you are doing a linear logistic regression, it's definitely a linear decision boundary. Okay, you cannot have nonlinear here. Okay, you won't have some decision boundary like this. It's impossible. Okay. So the linear boundary has some issue. I think you definitely notice if the data is linear separable. So we call the data linear separable if the data can be divided by a linear line. Okay, so for example, these two examples, the square and triangle, they are linear separable. But there are many cases the data may not be linear separable. Let me give you an example. For example, you have a lot of triangle like this, and you have some square in the middle. So this is a clear pattern, that is, you don't have a linear decision boundary to separate the data, but you actually have a nonlinear decision boundary. For example, you can just do like this. You have this decision boundary, but it's nonlinear. Okay, so you can see that the single neuron can only give you a linear decision boundary. For the nonlinear decision boundary, you cannot use, so no matter what type of activation function you use, you cannot use single neuron to provide a nonlinear decision boundary. Okay, so how do you get a nonlinear decision boundary? So you can see this, this is an example. We're talking about AND. This is an AND operator. So AND operator basically says x1, x2 has 0 or 1. So 0 and 0 AND, so it's 0, 0 and 1 and 1. So, sorry. So these three are all linear separable. Okay. So I give you another example, which is called XOR. Not sure you heard about this operator. So XOR is basically 0 and 0 gives you 1. And 0 and 1 gives you the 0. So basically you have two square here and you have two rectangle here. Okay, so you can see that this one is not linear separable. You cannot find a linear line to separate the data. But what you can do is that you don't plot the coordinate based on x1 and x2. You plot the coordinate based on AND. Okay, so that means you first apply an AND operator to x1 and x2, and then this data becomes linear linear separable. Okay, or let me give you another example like this one. This one is not linear separable, right? But if this data is, if we have a z coordinate, so it's difficult to draw. If we have a z coordinate, so say for example, our maybe I draw it in another one. If we have a z coordinate, so for example, the rectangle is on this level, and we have another level. We have some square in the middle. So if you look from top down, then it's not linear, it's not linear separable, but you can separate the data by using this linear line and this linear space. Okay, so it's difficult to understand. My drawing is not very good, but in general, you can see that what we can do is that we can first transform the data. And then after the transformation, the data can be linear separable. Okay, so we can do some transformation first, and then we check the separability again. So here you can see that we need some further transform of the input into a better representation. Then you'll find it separable. Okay, so why we're talking about this is because here you can see that you have the original data. So for example, I want to do a classification. So here, you have a neuron and you have an output. So here I'm saying that this output is not separable. You cannot get a very good decision boundary from this output. Then what you can do is that you can have another layer. So for example, here, you can have multiple neurons here. right? So it's the second neuron, and then third neuron. Okay, so here you can see that you have 3 outputs. Then I can treat these 3 output as the input of next layer. So we call this a so here we call the first layer we call it input layer. And then you can have one hidden layer, and then you can have the second hidden layer. You can have another layer. So this layer is similar that you can, for example, you can have, let's say we have 2 dimension. Then you just okay. So you can see here for this neuron, we take the 3 output as input, and then we have one more output here. We have one output here. And for this one also, we take 3 input, and then we have one output. So you can see that eventually we have the output of dimension 2. We call this a output layer. Okay, so how many neurons do we have in this figure? Basically, we have 5 neurons, right? So here you can 1, 2, 3. So each of the neuron has 3. This neuron has 4 input, 1 output. Okay, so this one output gives to is duplicated and gives to two different neurons. Okay, so basically you have this output, and this output goes to the two location. Okay, and similarly you have this one. You have 3. So basically you have 1, 2, 3, 4 input, and this one is also 4 input and also 1 input output. So you can see that each of this microstructure is a neuron. And by combining the neuron, and very importantly that we put the neuron into different layers. This is one layer, and this is another layer. Okay, so you can see that by having this layer, we can make the input of the output layer. So the input of output layer is actually the output of the hidden layer. Okay, then you can have the output here. Okay, so here you can see that I'm using 5 neurons to formulate a structure. And this structure is nothing new, it's just plus and minus and and also activation. Okay, what you are doing is very simple. You're just doing a summation, activation, then you output. Summation, activation, output. And then you have 2 output. You use summation again, you activation again, then you output. Okay, so this is basically how you write a simple neural network. This we call it a neural network. Okay, so formally it's something like this. Okay, so you can see that I have d-dimension input, and then I input to one neuron, input to this layer, and I didn't draw the bias here. So actually you have some bias. So I think it's easy to understand what is bias. Okay, so you have some bias here, and also have some bias here, and then you finally have one output, or have 2 output, depending on yourself. Okay, so here you can see that we have 3 layers. We have name for the layers. We call it input layer, hidden layer, output layer. Okay. So here, I think I give you this figure. You can calculate all the, if I give you all the weight, I give you the input, you can calculate what is the final output, right? So no problem. So there are, I think I have example. Oh, sorry, wait a second. Maybe I show you the example later. So maybe I do this later. So later I'll go back to this. But I think now you roughly understand the idea, right? So I'm still using the notation A and A. So here I have a pre-activation, post-activation, and then we have a final output. Okay, so mathematically, if you write it, it's a little bit complicated, but I think you understand what's the meaning. Okay, so I can do 1 output. I can also do 2 outputs, no problem. Okay, very straightforward, no issue. So I can do 2 output, it's same. So you can see that this neural network can be multiple input and multiple output. Okay. Okay, so how do we do classification? So for the classification, we are using a very special activation function. We call it softmax. Okay, so softmax is also mentioned in the Wikipedia. So here you can see that is particularly put it here. This is a special activation. It's mainly used for classification problem. So classification problem is basically you want to output which class it belongs to, right? So essentially the final output will be K class. And then your output dimension will be K. This will be K dimension. Okay, and we see that each of the location is actually representing the probability of being this class. So basically we are estimate the conditional probability of the image being this class. For example, our input is an image, and then after the neural network, we finally have output a k-dimensional vector. This is k-dimensional vector. And then this vector indicates the probability of being each vector. So this is P. And then I think it's very easy that you can show that the summation of P equals 1. That's our requirement. So the probability of being different class, if you sum them together, it should be 1 because it's a probability, right? So how do we ensure the summation to be 1? We are using a very special activation. We call it softmax. What we are doing is also very straightforward. So if you think of the neural network output, so it can be A1, A2, all the way to AC. And what we are doing is that we are summation over all the C exponential of AC, and then A1, A2, A3. So basically we are, sorry, we will also take the exponential. So basically we take the exponential and then we divide it by the sum of exponential. Okay, so it's written like this. Okay, so this is also k dimension. Okay, so input k dimension, output after the softmax is still k dimension. And this k dimension, if you sum them together, it's 1. Okay, so this is strictly positive and sum to 1. And this gives you the probability of each class. So here you can see that if we want, if we have this multiple layer, what we have is that, say for example, given the first layer after the hidden layer, because this is just one layer, right? So you only have the linear decision boundary. So you can see that you have a linear decision boundary, and then you integrate this linear decision boundary. Then in the second layer, you can see that you may have a nonlinear decision boundary. This one is already nonlinear decision boundary. It's in the middle, it's larger, and the two part is smaller. Okay, so here you can see that by having multiple layers, we can develop, we can find a more complicated decision boundary for the data. Okay, this is because of the nonlinear integration of the nonlinearity, each layer by layer. Okay, so this is another example. So you can see that I have 4 neurons in the hidden layer, and each of the neuron gives you a linear decision boundary. But if you integrate them together in the last output layer, you can see that it becomes a nonlinear decision boundary. And this decision boundary is actually very useful for the data like this. For this data like this. Okay, so you can see that this is nonlinear decision. So the decision boundary is something here, right? So in general, you can see that. So in general, you can see that if we have more neurons, or if we have more layers, the decision boundary can be more complicated, right? So remember that I mentioned every time, given a neural network, given a machine learning method, you should always be able to adjust some parameter from underfitting to overfitting. So for neural network, there is one choice that you can choose the complexity or number of neurons of your neural network so that it can be underfitting or overfitting. Okay, so neural network actually there's a lot of parameter you can do that, but number of neuron and number of layers is actually one issue. Okay, so this one is not very useful, but I should mention. Okay, so basically in the past there are many people they try to prove that. So we call it a universal approximation. Basically, it says that if you are using a single hidden layer neural network, means that something like this. This is single hidden layer, okay? And if you have enough hidden unit, means that you have more hidden unit here, then this neural network can approximate any continuous function arbitrarily well. Okay, so means that you just give me a function f. Okay, you give me a function f, and as long as I have one hidden layer neural network, and as long as I have enough hidden units, then I can ensure that this neural network can approximate f. Okay, so this is called universal approximation. So this demonstrates the capability of neural network. Okay, so there are many proof, and also similar proof says that if you are using sigmoid, it's also okay. If you are using tangent H, if you're using ReLU, if you're using different activation function, it's okay. Okay. So what's this function talk about? So if you still remember what is supervised learning, supervised learning basically we want to find a f such that if you input x, that you get y, right? So that basically says the universal approximation theorem says that you can always use neural network as f. It's arbitrary. It can be always a good choice, right? Because you can always so it can approximate arbitrarily well. Okay, you don't need to worry about whether the model is strong enough or not. So this theorem basically tells you that the neural network is super strong. It can definitely is capable of simulate this f. Okay, so but the issue is that here the universal approximation theorem just says that it can, but it does not tell you how. Okay, so it does not tell you how to find such a neural network to approximate f. Okay, so the next part, basically we were talking about more about how we find f. So before that, I have some notation or terminology to talk about. Okay, so here you can see that this universal approximation theorem says that you have you basically have a neural network, and you have the input, and then you have a hidden layer, and you can have arbitrary number of units in the hidden layer, and then you have output layer. Okay, so something that I want to highlight is that so how do you decide the dimension of each layer? How many units are there in each layer? So for the input layer, it's not decided by you. Okay, it's decided by the data. What is the dimension of your data? Then this is your input layer. Right, so this is defined by data. Okay, so here, what is output layer? How do you determine the output layer? This is defined by task. What you are going to do? You are going to do a K-class classification, or you want to do a regression, or you want to do a binary classification. So depending on what you want to do, the output will be different. Right? For example, you want to do K-class classification. you want to do k classification, then your output will be a k-dimensional vector. If you want to do regression, then, for example, you can regression for next 5 minutes. Then this is a scalar. Okay, so if you want to do a regression for next 5, 10, 12 minutes, then it can be a vector. Each number indicating 5 minutes, 10 minutes, 15 minutes, 20 minutes. Okay, so here you can see that what you want to do gives you the output dimension. These two parts you cannot change. Given a task, these two already determined. What you can change is here. Okay, so you can decide how many units you have in this hidden layer, right? And also, actually, I may not, it's not necessary that we only have one hidden layer. We can have multiple hidden layer. For example, you can add one more hidden layer like this. So nothing changed, right? So as long as you make sure the input output doesn't change, I don't care how many neuron layers or how many new units that you put in the middle. Okay. So I have two choices. So one choice is that I put a lot of neuron in one layer, or I can use multiple layers. Each of the layer I have some neuron. Okay, so that gives you two options. So here comes the terminology. Okay, so we call this as the depth of neural network. Okay, how many layers you have, this is called the depth of neural network. And how many neuron you have for each layer, this is called the width of neural network. Okay, so then question, so what is deep learning? So what type of neural network is deep learning? So when we talk about deep, so deep learning is basically talking about using the neural network that is using some deep neural network. Okay, so the question, how deep is deep? How deep is defined as a deep learning? How deep is, what is a depth that is not deep learning? What is a depth that you think of it as a deep learning? So what? More than one. So that's actually a good point. So so there's no clear definition, but the current one is basically says that as long as you have more than one hidden layer, it's deep learning. Okay, so the requirement is actually very low. Okay, if you just have two layers in the middle, then it's deep learning. Okay, but this is way more than what the deep learning that's in your mind. Okay, say for example, the GPT has hundreds of layers in the middle. Okay, and so usually when we talk about deep learning, it's actually much more deep. But technical definition is that 2 layers is deep learning. Okay, 1 is not. Okay, then I just want to mention a little bit more. So then I can develop 2 types of neural network. I can develop one neural network like this. So you have the input and you have output. I can have one like this. Okay, or I can have like something like this. I can have more layers. So this is one layer with a lot of neuron. This is more layers. Okay, we call this a wide neural network. We call this a deep neural network. Okay, so wide neural network and deep neural network. There is a very famous paper called Wide and Deep Neural Network by Google. Okay, so wide and deep neural network. This is a very benchmarking paper that is in 2016. So you can see this figure. So you can see here, this they call it a wide model. Okay, so you have multiple inputs and goes to one, and you can have a deep model that is something like this. Okay, and you can have a wide and deep model that gives you part of this and part of this. Okay, So question, what type of data is suitable for wide model? What type of data is suitable for deep model? If you still remember, we have talked about the sparsity of the information, okay? The density of the information given the feature. For example, the image, each of the feature, each of the pixel, the information density is low, right? The information density is low for each of the pixel. But if it's some, for example, user's name, user's age, user's gender, some category, the information density is high. Okay, so here in this paper, basically they talk about these two version of the this two type of data. If it's low density information, the wide model will be better, right? Because I'm trying to aggregate the information. And if the information density is high, then I want to use this kind of deep model so that we can have some more embedding, have more interpretation of the data. Okay. So if you read this paper, this basically talking about this one. Okay. It's talking about for images, you should use wide model. For the numerical numbers, you should use deep number, a deep model, and you integrate them together, you can have a better result. Okay. So we talk about deep and wide. Those are terminologies. Okay, so at least you know what is deep. When we talk about deep, what we are talking about. When we talk about wide, what we are talking about. And so so basically in the modern papers, if you read some neural network paper in recent years, no one will draw something like this. This looks stupid. A lot of neuron. Okay, so this is very old-fashioned. No one want to draw this. Okay, what we want to draw instead is something like this. Okay, so we just use this rectangle to represent different layers. Okay, and the weights of the rectangle indicating how many neurons that you have. Okay, so this is a recent approach to draw, and I think from this paper you can also see. So I'm drawing. So here you can see that they're trying to draw something like this. Okay. So later, if you write a neural network paper, so don't draw something like this. It's very old-fashioned. Okay. So if you draw this, then I think you just learned the very basic neural network. You haven't read any neural network paper in recent years. Okay. Maybe I show you some example. Okay, so this is very old-fashioned approach to draw. Okay, so don't draw something like this. Okay, it's not good. So all those that you can see, they are so old-fashioned. Okay, so what is a recent approach is something like this. So you just use this rectangle to replace. Okay, something like this. This is not a good example. Okay. So maybe later I show you more examples. So we just use this rectangle to replicate because now there are so many layers. If you just draw these circles, there are so many circles. Okay, maybe I show you another very important paper, ResNet, residual neural network. You can see this has been cited for 0.3 million, 300 some K numbers. Okay, the very famous paper. I'm not sure you know the first author, He Kai-ming. So very famous paper, and you can see this is a typical way to draw it. Okay, so because it's super deep, so if you draw circles, there's so many. Okay, so people like to draw like this. So this paper is already, I think, 10 years ago. Okay, so if you still draw something that is circle, basically means that you are using some neural network 20 years ago. Okay, so don't do that. Okay. So then let's talk about some terminology. So the first terminology we call, so something like this, you can see that I just draw here. It basically is that you have some input layer and eventually you have output layer and you have layer by layer, these hidden layers. This we call it a feed forward neural network, short as FNN. Okay, and this is also called MLP, multi-layer perceptron. I think this name is very easy to understand. You have basically have multi-layer perceptron. Okay, very straightforward. So in your if you are using PyTorch or TensorFlow, this is also called dense layer or linear layer, depending on which software you're using. Okay, so basically, no matter dense layer, linear layer, FNN, MLP, it's referring to the same thing. It's basically layer by layer calculation, and each of the layer is connected like this. Okay. And if you draw this in a neural network, in a rectangle approach, it's basically like this. Okay. Maybe usually we don't draw the first layer. The input layer we don't need to draw. We just say X input, and then eventually you have FX. Okay, 3 layer. We just draw this layer, and this layer. Okay. Okay. Good. Any question? Okay. So how do you, so let's say basically the neural network, if you want to evaluate, there are 2 steps. First, you need to calculate the answer. We call it forward. Okay, and then you need to update the neural network. We call it backward. Okay, let's first talk about forward. Forward basically says that you suppose all the parameters, all the weights and the bias that you already know. So basically you know everything here. And then given a x, how do you calculate fx? So this is super straightforward, right? So let me give you an example. Here you can see that my input is 1 and -1, and I have some weights here, and I have some bias here. And what you calculate is very straightforward. So 1 times 1, -1 times -2, plus 1, so it gives you 4. And you input this 4 to the logic sigmoid, you have 0.98. And similarly, you have 0.12. Okay, once you have this 0.98 and 0.12, you can input to the next layer. You can calculate this one, and then you calculate the final one. Okay, so basically, what you have for this whole neural network is that this neural network as a function f, the input dimension 2, output dimension 2, and then the input is 1 minus 1, output is 0.62.83. That's it. Okay, so very straightforward. Okay, but this is for illustration. Okay, if you write a neural network in your computer, it's not calculated like this. Okay, this is calculated by neuron, which is actually not the true way to do it. What we should do is that we should do it by So what is inside the neural network? For example, you're using PyTorch or using TensorFlow. What it's actually doing is actually calculate directly by layers. Okay, so let me show you. So here your input is x. Okay, so x is actually a vector, 1 minus 1, right? So I can organize the layers. So for example, so here I can have the W1 here. What is W1? The W1 actually is 4 numbers, 1, -2, 1, and -1 and 1, right? So it actually gives you a 2 by 2 matrix, right? So basically you have 1, -2, and -1 and 1. Okay, so what is actually happens in your computer is that what you are doing is that you find A1 is W1 times X, which is 1 minus 2 minus 1, 1 times 1 minus 2, 1. So what you have is 1 times 1 times 1 minus 1 times minus 2. And also you have a bias. So bias is 1 and 0. So you plus a bias, 1, 0. So you directly have, so we can calculate very quickly. So this is 1, 1, 3, 4. And this one is 1, -1. This is -1, -2, -2. Okay. Okay, and then you directly input H1. This gives you the sigmoid. You directly put in A1 in it, and you get 0.898, 0.12. So you can see that this is calculated by layer. We are not calculating one by one. We can use, you can see here, the trick is that I'm using the matrix multiplication. And then you can directly calculate the whole layer at the same time. Okay, it's a 2-layer. Okay, if it's a 100-layer, it's still a matrix multiplication. Okay, so this can significantly enhance the calculation speed. Okay. Okay. Good. Any question? And also, because of this, I think now you can understand why the neural network is better trained on GPU, because GPU is particularly good for matrix multiplication. Okay. So because all the operations on the neural network is in actually the matrix calculation, okay, then all those things, you can see that there's, if I write like this, there's no longer neurons, okay, just layer by layer and just matrix multiplication. Okay, so maybe I give you one more example. So let's say we have a 1000 dimension input as X. X is 1000 dimension. Okay, so let's say we have first go to a layer that has 128 unit, and then let's say the second layer is 64 unit, and then 32 units, and then 10 units. The final output is 10. Okay. So what is the matrix that you have? So have layer 1, you have layer 2, you have layer 3, you have layer 4. So input is 1000, right? 1000, you change it to 182. So here you have W1. W1 is this one is, so basically it's 128 times 1000. So this is W1. And also you have a B1 here. B1 is 128. Okay, so here from 128 to 62, then you have W2. W2 is 4 times 128. And B2 is 64. Okay, and then you can calculate what is the matrix that you have. Okay, so given a X, what you are doing, so layer 1, basically you are doing W1 times X plus B1 that you get H1, A1, usually they are using A. So you get A1, and then H1 is softmax or ReLU. So maybe let's use ReLU. So ReLU A1. Okay, so once you have A1, then in L2, it's basically W2 times H1 plus B2 equals A2, and then H2 equals ReLU A2. Okay, and L3, you can just write it. Okay, so you can see that the neural network calculation is just matrix multiplication, matrix plus, and just apply a function. ReLU function is super simple. You just check whether it's negative or positive. Positive, just leave it, and negative, make it 0. That's it. Okay, very simple. Okay, so this whole calculation is very straightforward. You just one by one you calculate, and here you can see that what I'm doing is just matrix multiplication. Okay, And here, from this setting, you no longer see neuron. There's no neuron, no concept of neuron. It's just matrix, matrix, matrix. Okay, so this is modern neural network. We're no longer talking about neurons. It's already like last century. Okay, so now if you think of neural network, it's just matrix manipulation. Okay, good. Okay, so maybe let's take a break and then we move to the next part. So this gives you the general idea of how you can calculate the forward path given a feasible for neural network, and also help you to understand how the neural network is related to the matrix calculation. Okay, so let's take a break. We will move to for 8 minutes, and we'll move to the next part. Okay. Okay, so let's move on. So I think from my previous description, I think you'll notice that there's a very important feature of neural network that is flexible. Okay, so what by flexible, basically I mean that as long as you give me the input and output dimension. Okay, so this is a data dimension, this is output dimension. So in the middle, you can do anything that you want. Okay, so how many neuron in each layer is actually decided by yourself. Okay, so essentially you just choose. For example, you can choose to have multiple layers. It's okay. You can have fewer layers. It's also okay. Okay, as long as you don't change the input and output layer. So you have your brand new neural network. Okay, you can develop a neural network work yourself. Okay, so you can see that this is a super flexible mechanism. Okay, so this is a flexible design, and in addition to this, we can be even more flexible. For example, we need to go back to the neuron part. So we know the input neuron and output neuron. Okay, so for this neuron, so in the past we actually connect all this neuron to here, right? But who says that we need to do this full connection? What we can do, for example, this is arbitrary. Okay, so what I can do is something like this. I select some of the input to connect for the next layer. And similarly, what I can do is that I can do something like this. So you just do arbitrarily, it's okay, right? So you make your own decision which to connect, which to not connect, and how many layers, how many neurons. So as long as you make your decision, you get a new neural network. Okay, so this whole thing we are talking about the structure of neural network, or sorry, architect of the neural network. Okay, so basically you can develop a new architecture of the neural network. So this involves how many neurons, how many layers, how they are connected. Okay, so these are all on your decision. As long as I don't change the input and output, those neural network gives you different different structures. Okay, so the question is basically so here let me show you the slides first. So you can see here, this is the original traditional one. Okay, we call it so I think now you understand what is fully connected mean. Fully connected means that all the neuron here is connected to here, and all the neuron here is connected to here. So fully connected. Okay, if there is fully connected, I can do partial partial connectivity. This is an example. So you can see that I do fully connectivity for the first layer. Okay, then second layer, I do a partial connectivity. So it's all by your design. So you can design. So for example, if you have some physical meaning of here in your domain, if you have some physical meaning of the data feature, then you may understand that you don't need to do the fully connectivity. You may want to do some other connectivity. Okay. So here is some other example. Okay, so here you can see that I can do fully connectivity. I can do some some partial connectivity. So it's all your decision. So all this we have 3 different neural networks here, but all these 3 neural networks they can fulfill the same task, because sorry, this is not different. This 2 is the same. Okay, 4 in, 3 out. No matter what happens in the middle, we don't care. We only care about what is the input, what is the output. So for the middle, we just want to have a good one. Okay, so basically, I think you definitely heard about the neural network is a black box. We do not want to explain anything in the middle. It's meaningless. Okay, so you don't want to explain why is this connectivity, why this connectivity. It's completely meaningless. So no one want to do this because basically these are numbers. Okay, so from my previous description, I think you also see that it's meaningless to talk about why these are connected or why these are not connected in the middle. Okay. So I think having this, the first thing, so no matter what type of the neural network that you have, one of the issue or one thing that you need to do, or you need to you should be very familiar in that I gave you a neural network. You can quickly calculate how many parameters are there in this neural network. Okay, so when we talk about parameter, there are two, as I just mentioned, weights and bias. Okay, so what is a weight? So let's try to calculate this one. What are the weights? So this has a W1, this has W2, this has W3, right? So the W1 will be 4 by 3. W2 will be 3 by 4, and W3 will be 4 by 3. Okay, and also you have B1, B2, B3. So B1 should be 3 dimension, B2 should be 4 dimension, B3 should be 3 dimension, right? 3, 3, 4, 3. So this one is 12, 12, 12. So in this neural network, so how many parameters that you have? You have in total 46 number of parameters in this neural network. Okay. So I think you still remember what is hyperparameter, what is the parameters. So in this neural network, the hyperparameter are number of neurons, what are the architect, what are the structure, and the parameter are the weights and the bias. Okay. Okay, so okay, so I think I already say this is very flexible, and then you have the input X, and then eventually you have output Y, and in the middle you have layers, right? So back in, I think 10 years ago, okay, so there's a bunch of people that, so the neural network start to be very popular starting from 2011, because 2011 is the very first neural network that becomes very, very good performance, okay? So in the 2011 to 2020s, I think, so in this past 10 years, in that decade, so there's so many people, they try to develop different layers. So as I just mentioned, you can see that you can do arbitrary design, right? And some of them becomes very useful. Okay, people show that they are very useful. So essentially, we have a toolkit. So nowadays we have a toolkit. So there is a bunch of layers that has been tested for years. And these layers, they are good and they are useful. Okay, so you ask me why this layer are useful. They have some explanation, but those explanation is just explanation. Okay, so no one knows why it works well. Okay, but I think I talked to many people. So deep learning is very similar to Chinese medicine. Okay, so basically you find this particular medicine that is useful because it's useful. Okay, so you never know why it's useful, but it's just useful. Okay, so it has been years demonstrated that this is useful. Okay, so if you want to do a lot of deep learning research, the first thing you need to do is that you need to enrich your toolkit. Okay, means that you need to know as many as possible layers that you can use in your neural network. Okay, for example, we just talk about MLP. Multi-layer perceptron is one layer, one particular layer, or we call it a dense layer, or we call it fully connected layer. It's the same. Okay. So this is a very basic layer that we have. Okay. Then you should have more layers to choose from, right? So there are others. For example, there's a layer called convolutional layer. This one has been demonstrated extremely useful for images. Okay, extremely useful for images. So later we'll talk about more details, but why it's useful. They have some explanation, but it's just explanation. Okay, and there's another one called recurrent layers. Okay, recurrent layers is particularly useful for time series data. Okay. And there's another one called GNN, graph neural network. And in GNN, there are so many layers. Okay, so why it's called neural network? Because there are so many layers in the graph neural network. But in general, these are very suitable for network data. Network data means that each of the data has some relationship. For example, social media. If each of the user they have some relationship, this is called network data. So network data, for example, gene, and also your like transportation, the road, and social media, and I think as long as the data contains some relationship, network the GNN will be very useful. Okay, MLP, CNN. So here you have CNN, RNN, so convolutional neural network. So if a neural network contains a lot of convolutional layer, then we call it convolutional neural network, CNN. If a neural network contains a lot of recurrent layers, we call it recurrent neural network, RNN. Okay, if a lot of a network contains a lot of graph-related layers, we call it GNN, graph neural network. Okay, so these three, I think, covers most of the data type: image, time series, network. You just think of the data that you are using. Which one is more suitable for you? Okay, so image is more. So basically, image by convolutional layer. Time series contains voice, audio, language. They are all time series. It's a sequence. Maybe I shouldn't say time series. This is a little bit tricky. I should sequence data. Data is in sequence. Then it's very suitable for RNN. Okay. Okay. So that these are basic layers. So say for example, I show you some example. I show you some data type that is more tricky. Say for example, a movie data or video. What's the video data about? Video data is image, right? And it's a sequence of image. So the video data is actually sequence data and image data. Then how do you do? Then what you can do is that you can, for example, you input a video. What you can do that you can first have some convolutional layer, and then you put it to RNN, recurrent layer. So you can combine the convolutional layer and the recurrent layer to process this kind of sequential image data. Okay, it's possible. Or we think of another one. So in a building, we have a lot of sensors. Those sensors provide the time series data, but those sensors they also have some relationship on the building, right? So this one is actually you can use GNN plus RNN to process this type of data. Okay, so depending on different type of data, you can actually use different type of neural network to process it. Okay, then let's talk about more complicated one. Say for example, I have a image, and then I have some description of the image. So description data is language, right? Language is sequence data. Image is image data. So what I can do is that I can put the image into CNN first. I can put the language to RNN first, and later I can combine them together to output. Okay, so you can see what I'm doing here. We are talking about neural network structure design. Okay, depending on the data structure that you have, depending on the data source that you have, you can design this kind of neural network by yourself. Okay. Okay, so I think there's one more layer that I haven't mentioned, which is the recent one, transformer. Okay, transformer, you know what is GPT, the T refers to transformer. Okay, transformer is a very recent layers, and basically the transformer is good at all the data above. Okay, it can be used to tackle the image data, can be used to tackle the sequence data, and it can be also used to tackle the neural network data. So it becomes a universal structure that can handle different type of data. Okay, so this gives the theoretical foundation of the current ChatGPT. Okay, because now the ChatGPT you can use image, you can provide a language, and also you can provide any data to the ChatGPT. It can understand. It's mainly because the underlying structure, the transformer layer has this capability. Okay, but it has a cost. Everything comes with a cost. Okay, do you know what's the cost of transformer being so capable? It requires a lot of data. Okay, given, for example, if you want to use transformer and convolutional layer to learn an image, if the convolutional layer requires much fewer image. Okay, so everything comes with a cost. There's no free lunch. Okay, so for example, in your engineering application, in your case, if you have some special application that you want to use, in many cases, engineering problem does not have so many data. And in that case, maybe the transformer may not be the good choice. Okay, it depends. It's not saying that the transformer is always good. It's not the case. Okay, if your data is very limited, transformer is actually worse than you are choosing a very suitable layer. Okay, so so in your research, for example, you do have some problem that you want to solve. My recommendation is that I highly suggest that you don't develop a neural network structure yourself. Okay, similar to Chinese medicine, you don't want to develop a new dose yourself. You just want to combine the existing ones. Okay, for example, you have an image, then you just use the image module. If you have some data, you just use the corresponding module. And people has already been trying this kind of neural network structure for a long time. Okay, so just choose the good one. Okay. And I think in the past 10 years, there are so many papers on the neural network structure development. Okay, so nowadays, I think there's already a lot, and it's very hard or it's very difficult to claim that you have some contribution on designing a neural network. Okay, so for example, in your paper, you said that you have developed a new structure of the neural network. This is very weak. Okay, so try to make your contribution more. So don't put your contribution onto the neural network structure design. It's very stupid. Okay. Okay. So there are already a lot of those in the that you can choose. Okay. There are a lot of combination that is very has been tested for years that has been very useful. You just use them. Okay. Okay. So here I just list the most the commonly used one. Okay, so there are actually much more than this. Okay, so for example, there are a group of neural network called FNO. Sorry, NO. There's no F. NO called neural operators. This is particularly useful for processing the data that is generated by partial differential equation. Okay, so it's very tricky. You can see that the data. So maybe you haven't heard about what type of data is generated by partial differential diffusion, partial differential equation. For example, wind. The fluid dynamics is based on the Navier-Stokes equation. It's actually a partial differential equation. Okay, So in different area, they have their own layers that they like to use. But what I just want to say that this area is very crowded. Okay, it's very difficult to develop a new layer that has been proved very good. So if you want to publish a paper for developing a new layers, you have to compare a lot, which is not very cost effective. So I highly recommend you don't do this. Okay. Okay. So you need to make sure that you know as much as possible. Otherwise, what you have developed is just a repeat of other people's work. Okay. Okay. We talk about layers. So we talk about layers. This is so the smallest unit is neuron. So neuron formulates layers. Okay, and layers, if you integrate layers, comes with module. This is also terminology. Okay, so I have some specific combination of the layers. This gives you a module. Okay, say for example, transformer. Transformer, I think you know this famous paper, attention is all you need. Okay, you know this super famous paper, okay? For this paper, you can see that this structure is basically a transformer architect. Okay, so you can see that this basically, maybe now I think you can roughly understand what it is. You have some input, okay? You input, you add something, and here you run a attention, and after the attention, you just run a MLP. You know what is MLP already. So feed forward is basically feed forward neural network. So this part is a neural feed forward neural network. And then you do some add and now layer normalization. And then you just have something like this. And you also have a feed forward neural network. And finally have a linear layer and you run a softmax, you get the output. So you can see that this is a particular combination of some layers. And this, we call it a transformer. So transformer is a module. Okay, it's similar to Chinese medicine that you have multiple herbs and you combine them every time you use them together. So it becomes a module. Okay. So then given the module, we also talk about there's also next one is called scheme. For example, scheme, what we have, for example, we have just a supervised training scheme. And maybe we have some other scheme like the, maybe you haven't heard about it. Have you heard about GAN? Generative Adversarial Neural Network. Yeah, something like that. That is more like how do you use the module to particularly design your neural network. Okay. So basically these are the order. Okay. So what I recommend is that you don't do any contribution on this part. Okay. It's very difficult. What you can do contribution is here. Scheme. Given your data, what type of training scheme or model scheme that you can develop. And this scheme consists of a lot of existing modules. Okay. Okay, so then let's spend some time to talk about some very famous neural network I shouldn't, maybe this is a module or this is a layers. Okay, so CNN is a very famous one. So this is extremely useful for image related data. Okay. So CNN, why we need a special module for CNN for image? So here, this is mainly originated from computer vision. So you know computer vision is a super large area, right? So basically the key issue that the input will be an image or it will be a video, and then the output is something that you want to understand this image. Okay, so there's a very typical standard task. We call it object detection. Also, image classification. It's basically I give you an image, and then you tell me what class it belongs to. For example, I give you 1,000 class, and you just tell me which one out of this 1,000 class, which one it is. Okay. So I think now you can develop a neural network for this. Okay. So what is the input dimension for this image? The input dimension is 100. This is 112 pixel times 150 pixel, and this is color image. So it's three channel. So this is your input dimension, right? And then you just put some layers here, and eventually, I said it's 1,000 class, right? So the last layer will be 1,000. Okay. So basically, input dimension, output dimension is fixed. Input dimension is 115 times 150 times 3. Our final dimension is 1,000. Okay, you just arbitrarily input in the middle. Okay, so maybe I just do a quick one, 10224, maybe 512. That's it, and then the too small. Maybe this is 3072, 1024, and 1000. Maybe 2048. Okay. So you ask me how I decide this number. It's hard to tell. Okay, so by experience. Okay. So then let's calculate how many parameters do we have for this neural network. So W1, what is the dimension of W1? This will be 3072 times 115 times 150 times 3. Okay, so how many? Let me calculate. 3072 times 115 times 150 times 3. So this is roughly 158 million times 10 to the power of 6. Okay. So do you know how this is number of parameters that you have, right? Each of the parameter, I forgot if I show you or not. One parameter, usually we are using float 32. Do you know this? How many memory that one parameter take in your computer memory? We are using float 32 means that this takes 4 bytes. Okay, so 4 bytes. So that means you need to store this matrix. You need 158 times 10 to the power of 6 times 4 bytes. So 1024 bytes is 1 KB. Right? So how many KB? So I can quickly calculate. So 600 times 1 times 1 power 3 KB. So how many? So this is 600 megabytes. Okay, so this is roughly 0.6 GB. Okay, you can see that this single matrix already takes 0.6 GB in your computer. It's actually super large. It's already very large, right? And here I'm talking about 100 pixels or something. Okay, the current image is usually 1020 times 1960, something like this. So basically, so you can see that if you are using the MLP, it's almost impossible to process the image data because the dimension is so large. Okay, then the question is, why do we need to do the fully connectivity? We don't need to do fully connectivity, right? We can do partial connectivity. Okay, so to process this type of data, so here I just mentioned, so you have a lot of high dimension. So in the CNN, there are some of the key idea that has been used. The first key idea is called local connectivity. It's basically a partial connectivity. Basically, what it says that you can, because the image, the pixels, they are actually related only when they are nearby. So what we can do is that we can only look at this area. So in the past, what we are doing is something like this. So all the pixels connected to one single layer or one single neuron. We don't need to do this. We only need to let this part of the pixel connected to this neuron. Okay, so this is local connectivity. Okay, so what we want to do is something like this. Okay, so by doing this, you can see that you can largely reduce the parameters because the connectivity reduce a lot. And this area, we have a name, we call it a filter. So we call this neuron, a particular name, a filter. And this size 10 by 10 basically says that in this image, we just look at this 10 by 10 area to do the connectivity. Okay, this filter, this term comes from the traditional image processing. Okay, so they just use the same word. Filter in Chinese 滤镜. Okay, I think a 滤 or filter, yeah, something like that. Okay. Okay, so this is the first idea, local connectivity. So this can reduce a lot of parameter, but it's still, so that it has been calculated for you. So there are still 4 million parameters. So in the past it's 100 million. So now it's 4 million, but 4 million is still not that, it's still many. Okay, what we can do, the second idea, this is also commonly used in many neural network structures. The second idea, we call it parameter sharing. Parameter sharing says that, so here you can see that different connectivity, I'm using different weight. So here we have W1, here we have W2, right? But what happens if we only use W for both? We use the same W for different neurons. This we call it parameter sharing, share parameter among neurons. Okay, so that basically says that if you have different filters, and we are using the same weight, we don't use separate weight. Okay, so here, technically what we are doing here is that given this whole image, we use W to calculate here. We use W to calculate here. We use W to calculate here. We use the same W to calculate everywhere. So in that case, you only have very limited number of parameters because you only have one W, but it can be used for everywhere. So this is parameter sharing. Okay, so you combine the local connectivity and the parameter sharing, and then we talk about the third idea, which is a approach called convolution. Convolution is a calculation approach. Maybe I skip the detail. Okay, so basically what we are doing. So finally, what we are doing is like this. So you can see that this is an image. Okay, and then we have a filter. This is a 2 by 2 filter. Okay, what we are going to do is that we will use this filter to calculate for this part. So usually, I think it's 1 times 1, 0 times 0, 1 times 40, and 0.25 times 20, 0.5 times 80. So use transform. Or you can use this one times this one, this one. So there are two versions. Okay, so I think here we are using the transverse version. So basically you transpose, and then you multiply each by each, and then you sum together. This gives you the first number here. This gives you this number. And then you use this to calculate with this 4. You get this number. Okay, and then you just keep calculating. You have this number and you have this number. Okay, so you can see that this whole approach, we are using, you can see that we are using the same weight calculating for different location. And also we are doing a local connectivity. So we are together using convolutional operator, local connectivity, parameter sharing, so that we can get this final results like this, and eventually this. So by doing this, you can see that we are using a filter. We're using this as W. We can convert this image to a smaller image. So this process we call a convolutional layer. So this whole three things together, we call it convolutional layer. Maybe another example. So here you can see that we are using this as a weight W. And then what we are going to do is that So here you can see that we are using 0.5.5, and we move to here. And then this part, 0.5, 100, and we get 128. And this, we get this one. And this, we get this one. We just keep calculating. We have this whole matrix. Okay, so this whole process, we call it a convolutional layer. Okay, question. So here you can see that my input is d by d, say for example. And here is k by k. What will be the output dimension of this matrix? It will be d minus k plus 1, d minus k plus 1. Right? Yes. Yes. Okay. So here you can see that we slightly reduce the matrix output, the output. Okay. And how many parameters do we have for this layer? For this case, we only have 4 parameters. So only these 4 are unknown. So you can see that this largely reduces the number of parameters. And after that, usually, so here, after you calculate like this, we also remember that we also need to add some activation. So you can further run a sigmoid, for example, here. So it's very similar to linear layer. Linear layer is sum activation. So here is convolution activation. Okay, it's just the convolution a little bit complicated, but it's actually still simple, right? You just calculate the one by one. Okay. Okay, some special case. So what if you don't want to reduce the size of the output? So here you can see that the output size is actually reduced. So what happens if you don't want to reduce the size? What you can do is we call it padding. Padding means that you don't start from here. You start from here. You pad the 0 for this matrix, and then you calculate. So basically you make this matrix larger, and then the final output will be the same as the original matrix. Okay, so this is one technique. And so there are some terminology. So padding is one terminology. Another terminology is filter size. Filter size in this case is 2 by 2. It's basically talking about what weight matrix you are using. So in this case, we are using the weight matrix like 2 by 2. If we are using 3 by 3, it's here. Okay, so different weight matrix will make your output differently. The size will be different. Okay, so there's another concept called stride. I think from the name, you understand what it's meaning. Stride means how long you will take the step. So for example, here, every time we move one cell, we move by one cell. In this case, this is called stride equals to 1. What happens if stride equals to 2? Then after you calculate this, you calculate this one. This is stride equals 2. Then what is stride equals 3? You calculate this one, you calculate this one. Stride means next time how many steps that you move. Okay. So stride can help you to do subsample. Okay, if you use step equals to 2, you actually are doing subsampling. Or you think of downsampling. Okay, so this filter actually has some physical meaning. For example, I think in the past, many people, they try to develop different filters that they have different functions. For example, this is a famous one. So if you just use this filter to apply to this image will give you something like this. So it's more like some edge extraction. So there are actually, people are developing some different type of filters. So those are actually hard coding. So these numbers are hard coding, but the neural network can automatically learn those numbers. Okay, so basically it's learning the weight. The weight is a filter. Okay. Okay, so in this case, you can see that in a 200 by 200 image, if we just use 100 filters and the filter size is 10 by 10, so you can see that 100 filter by 10 by 10, this is just 10K parameters. And there's a very interesting observation is that this has nothing to do with the image size. Okay, so you give me any size of the image, I can still apply this filter. So this is independent of input size. This is a very important feature. If you look back to MLP, in MLP, everything is related to the input dimension, right? So you have to, the W1 is related to the input dimension. Okay, that means if you change the input dimension, the whole neural network has to be retrained. Okay, but this one is not necessary. Even though you change the input dimension, the filter, you can still use it. Okay, so this is a very good feature. Okay, so this feature allows a lot of, so it can accommodate different type of images. Okay, so there's a last technique, we call it pooling or subsampling. This is very simple to easy to understand. I skipped the mathematics. It's basically very straightforward. Pooling basically says that it has two versions. We call it max pooling and average pooling. Max pooling basically says that I just take the largest one out of this filter. For example, this 4, I just take 0.19. And this 4, I just take 0.19. And this 4, I take 0.75 and 0.02. That's it. Okay. Subsampling can largely reduce your image size. Okay. Why we are doing subsampling? There are several reasons. One reason is that if you think of an image, like something like this, if you reduce the size, actually it can be, so basically you are looking at a very abstract or very low resolution image. And this low resolution image, if you can perform well, then you can perform on the original image. So this actually tolerates some change on the local. Okay, and also this reduces the neural network size. Okay, so for example, your image is something like this. And if your image up, so if your image shift 1 pixel, shift by 1 pixel, this two, if you are doing the down sample, if you are doing the pooling, it gives you the same result. Okay, so combining the two, the convolutional layer and the pooling, we can have some neural network. We call this a convolutional neural network. So this is a very famous one. Maybe I try to explain this, okay? So here you can see that the input size, the input image is 83 by 83. Okay, then first thing, you apply a 9 by 9 filter, 9 by 9 convolution, and then you have 64 filters. So 83, 9 by 9, what is the output dimension? So 83 minus 9 plus 1, so it will be 75. Right, so here you can see that 75 by 75. This is your image dimension. Okay, and you have 64 kernels, means that you have 64 images. Okay, so here you can see that you have 64 images. Each of the image is 75 by 75. And then I'm doing a subsampling, 5 by 5 subsampling. So here, then I still have 60 image, but each of the image is downsized by becomes 14 by 14. Okay, then I apply a 9 by 9 filter again, but this time I use 4000. So 14 minus 9 plus 1, so it's 6 by 6. And I have, I think this is typo, sorry, this is 256. Then I have 256 number of kernels here. Okay, then I do a subsampling again, so it becomes 256, 626, I change it to 1 by 1, so it becomes 256 and 1 by 1. So 1 by 1 image is just a scalar, right? So here it becomes a 256 vector. It becomes a vector. And then here you can see that I run a MLP. So eventually I got 110, 101 output, dimension output. So here you can see that we are using the convolutional layer and also we are using the fully connected layer. So eventually our output dimension is 101. Okay, let's calculate how many parameters do we have. So how many parameters do we have here? So 9 by 9 by 64, right? So pooling, there's no parameter in the pooling. And then here, 256 by 9 by 9, okay? And here, this is MLP. How do you calculate MLP's dimension? So 256 times 101, right? Yes, okay. So, so I think, so let's do a quick calculation. This one is 5184. This one is 2736. This one is 25856. So you can see that from this, you can see that the MLP, even though we have already downsized the image a lot, the final layer is actually half of the parameter. Okay, so you can see in the, so even though this one is 25K parameters, this plus this, so the first layer just 5K. This one is 20K parameters. So you can see that how CNN is parameter efficient. And from another perspective, how the MLP is very intense, it actually contains a lot of neural net parameters. And it's actually universal. This issue is universal, even though for this transformer, most of the parameter is in the feed forward. Okay, it's mainly because the feed forward is a fully connected, so it's actually a lot of parameters. Okay. So we talk about CNN, then the next one is RNN. RNN, as I mentioned, this is particularly used for processing the sequence. So this is a neural network that is MLP. Okay, so you think of MLP something like this: you input something, and then you have some hidden layer, and then you have output layer. So I just make it narrow. Okay, but it's something like this: layer and layer, and finally output. So we call this 1-to-1. So you have one input and you have one output. What we have, what we can do is something like this. You can see that we have one input, and then for this output, we can make it for this latent neural network, for this hidden layer, we can make it output, and at the same time, it goes to next hidden layer, and this hidden layer goes to the second output, and then it goes to the third latent hidden layer, and then it goes to the third output. This we call it one-to-many. For example, I can input an image, and then we output a sequence of words. This is used to describe an image. So we are using this one-to-many structure. I have one-to-many, then I can have many-to-one. Okay, so many-to-one is similarly, you can see here, and then you have the latent hidden layer, and then finally you have output. So how do you, I think from this figure, maybe you don't understand how we do it. Maybe I draw it in a traditional way. So this is X input, right? I have a hidden layer. So this is my hidden layer. And for this hidden layer, I make it two parts. This I make it output. Sorry, Y1. And at the same time, I put it to, this is not it. I put it to here. This is my hidden layer 2. And then the hidden layer 2 gives you the second output, Y2. And then I put it here, and it gives you the third hidden layer, third output, Y3. So you can calculate this, right? Give you X, you just calculate what is this one, and then you put the input here, you get this one. And then you make the input here, you calculate this one, and then you can calculate this one. So this is also a very sequential calculation, but it's just a more complicated connectivity. Okay, so nothing new. It's still calculating from X all the way to Y, but this Y is a little bit more complicated. Okay, it's not a straight line. It's something straight line, and in the middle you calculate something, and then you calculate something back. But because the neural network is so flexible, this is definitely doable. Right? This gives you the recurrent neural network. And we can do one-to-many, many-to-one. We can also do many-to-many, so it's the same. Okay. Okay. So many-to-many has two versions. You can do you can have some delayed many-to-many, or you can have a synchronized many-to-many. It's the same. So I draw like this, and you can definitely build your neural network structure like this. Okay, so because this drawing is too complicated, so we have some simple drawing, is that we say that there are some internal states that they are recurrent. So basically we say that the RNN, the feature is that we have some internal state that is updating itself. You can see here, we have some internal state that is updating itself. So here we have some internal state that is updating itself. Okay, so I can draw like this, or I can draw it on road. It's something like this. It's basically you have X and you have R. And if you want to do many-to-one, you don't need this one. You just have this one. Or if you want to do many-to-many, something like this. Or if you want to do one-to-many, you don't need to have this one. Okay, so it's very arbitrary. You just design based on your need. Right? In essentially the key item for the RNN is that you have some internal transition of the hidden layer. Your hidden layer is updating itself. Okay, so this is a key function that is different from other neural network, that you have the old state, and then you have the new input, and you have a function fw that can update your new state h. So that means your RNN is maintaining a state ht, and this ht is updating every time. So think of this as some memory. Because this is sequential data, you have to memorize what happens before. Okay, think of this as some memory. So because this RNN, there's sequence. So it's not a one-time decision. So you have to have some memory in the middle. Okay. So once you have this memory, and then you based on this state, you can output something. Okay. So here you can see that we are using this H as a transition state, or you think of it as some memory. We keep updating this memory, and based on this memory, we output things. Okay. So this we call it a recurrent formula. So this is the most important part. So in the other neural network, we don't have this one, but only the recurrent neural network we have some state that is recurrent. And there's a very important issue that here we are using the idea of parameter sharing again. So here, if I go back to my drawing here, So you can see that here I'm using H1 to update H2. I'm using H2 to update H3. So I assume that the W here, I'm using the same one. Okay, so this is parameter sharing. So I can make it different, right? I can also make it same. The same means that I assume that the updating mechanism is constant. Okay, I'm using the same updating mechanism all the time. Okay. So here you can see that, this FW is not related to T. It's independent of T. So no matter which time you are here, which step you are at, we are using the same updating function. Okay, so for example, this updating function, I can use this one. So given the the old HT minus 1, I just multiply by a W matrix, H by H, time WHH, and then given the new X, I'm using this another matrix W. So this is similar to MLP, right? Then you just use tangent H, you update the H. And then given this HT, you use another matrix WHY, you get the output. Okay, so this is nothing different but a MLP. Okay, the only thing different is I'm reuse this three matrix. Okay, so if you don't know, if you don't understand this one, I draw the original one. So this is X. So this is H1, right? So H1 goes to H2. H2 goes to H3. And also we have X1, we have X2, we have X3. And H1 gives you Y1, H2 gives you Y2, H3 gives you Y3. So this is nothing different but an MLP, right? So for this first MLP, so you can see that you have H1, and usually we have a H0 as an initial. So H0, something like this. So you can see that you always have HT minus 1. So this is H0, H0, and X1. You put a function and you get Y1. Sorry, H1, sorry. You get H1, and H1. Then you have something. You use a layer to make it Y1, and here you make it Y2. So here you can see that you always have this something like this, and then what you can do is that you always assume W2H you have a WXH, and H2H you have WHH, and H2Y you have WHY. So you only use these three parameters. So no matter it's T equals 1 or T equals 3, so you always say that H1 equals WHH0 plus WHX X1. And similarly, H3 equals WHH H2 plus WHX X3. Okay, so here you can see that we are sharing the parameter. This is parameter sharing. In the original MLP, this should be different W because it's different layer. But here we do parameter sharing. Okay, so this can reduce the number of parameters, and this has interpretation. Basically says that the even though the time flows, the mechanism is the same. So you should use the same W. Okay. So this is a figure I just show. Okay, so you can see that you have like different W. This W is used everywhere. Okay, so you can see that it's used everywhere. Okay, so that gives you the structure for the RNN. So I don't have the time for GNN because GNN is so complicated. Okay, so I just recommend a a web, so if you are using the deep learning, if you are, want to write a deep learning package, what I highly recommend is just use PyTorch. I think you definitely know this, okay? So TensorFlow, recent years, not too many people use it. So if you start, I highly recommend use PyTorch, don't use TensorFlow, okay? So for PyTorch, there is a particular library called PyGeometric, PyGeometry, I think. This one, PyGeometry. So this one, not this one, sorry, PyTorch geometry. This one PyG. PyG, this is basically include most of the layers that are related to the GNN. Okay, so for example, you go to the neural network, and this has, for example, there's in the graph you can also do convolution. This we call it graph convolution. So here there's a list. Okay, so you can see how many. Okay, so each of the layer, you have a paper. Okay, so this paper shows how those layer is developed. So you can see how many layers that you have, even just for a graph convolution. Okay, so if you're interested, I highly suggest that you just read some of them. Okay, you read some of them, then you know that they're roughly similar. Okay, so it's very difficult to if you just want to use it, it's very difficult to identify which one is good or which one is not good. You just try all of them or try most of them. Okay, so so if you want to develop a new layer, what you need to do is you need to compare with all this. Okay, so that's why I highly recommend you don't do this. Okay, but you should enrich your toolkit as much as possible. So you should, if you have time, just read more to understand those layers. So those are GNN, graph neural network related. Okay, so for CNN and RNN, you don't need to use that. You just go to the PyTorch. Okay, so PyTorch. So there's a document. Okay, PyTorch document. And if you want to look at layers, you just go to the torch NN. And here you can see that they have a lot of layers. The convolutional layers I just mentioned, pooling layers, padding, I just mentioned padding layers. How do you do padding? And recurrent layers. Okay, so recurrent layers, there's also a lot. And like I think I mentioned some. Okay, so for example, convolutional layer, I give you the idea of 2D convolution, but it's very easy to extend to 3D convolution. And there are some other convolution. If you're interested, you just go to here, and then it will give you the equation and how you use it, and give you some example. Okay, and so those are the very famous one. And pooling, you can do max pooling, you can do average pooling, and there's some other pooling. You can just look at and padding, how do you do padding? And the recurrent, what I just mentioned is called RNN, the simple RNN. Okay, there are two famous RNN I haven't mentioned. One is called long short-term memory. Maybe you heard about this. Okay, LSTM. So this is the equation and this is a paper. Okay, so basically it's it's a little bit different updating mechanism, but the idea is very similar. And there's another famous one called GRU. Okay, so GRU is a gated recurrent unit. So this is equation and they have the paper. Okay, so transformer I haven't talked about. Okay, if you're interested, you should read this part. But transformer has a new package which is called transformers. Okay, so this is the one that contains a lot of transformer related packages. Okay, so it has another name called Hugging Face. I'm not sure I heard about this. Yeah, so so this one is transformer. So basically, you can see that the traditional classic one you can directly use PyTorch, and for the new layers, GNN you should use this one. And transformer, you should use Hugging Face. Okay, there are others, very advanced one. Maybe I just let you know. There's one called Pyro. Pyro, Pyro. So if you want to use deep learning for probabilistic modeling, this is a package. Okay, so for example, here they have some neural network that is very tricky. For example, they can do Bayesian neural network that incorporate the Bayesian analysis into it, or they can do. So this one is I'm not very familiar, but this one I'm not sure Professor Zhang talked about elbow or not. Or have do you know what is variational inference? So there's a group of people doing integrating probabilistic modeling and neural network. It's basically this one. Okay, so basically based on the PyTorch as a foundation, there's other packages that's built on top of it. Okay, and depending on your need, you just try to look at different packages. Okay. Okay, so we have already talked about everything, how to build a neural network. Okay, then the only thing remains is how you train a neural network. Okay, training a neural network is basically solving a optimization problem. So I think you already know this, so I don't need to talk about this too much. So basically, I think I skipped this part. Later, if you're interested, you can take a look. Okay, so when we talk about training a neural network, basically we are talking about, so given a neural network, eventually you need to calculate a objective. And this objective, we call it loss. For example, for the supervised learning, your objective is the difference between the ground truth and your answer. For example, you have y equals fx, and the final, the loss will be y minus fx and something like this. Okay, so this is basically your objective. You want to minimize the loss. Okay, so different task has different loss, but for the supervised learning, most of the loss is minimizing the difference between the answer and your neural network. Okay, so what we are actually doing is that we define, we think of the loss as an objective, and what we want to do here, you can see that we want to minimize the difference between the neural network output and the expected outcome. So particularly, we want to minimize the neural network. You put X into the neural network and you compare with Y. You define the L as a loss, and then you sum all the data. And this gives you the total loss, L theta. So I think last week we talked about this term. So this is basically an empirical risk minimization problem. Yes, good. So basically, when we talk about training a neural network, we are talking about finding the parameters. We are talking about finding the weights and the bias. And we are talking about, we want to find the parameter theta such that the loss is smallest. All right. So basically, you can see that we want to solve a optimization problem. Then we find the parameter theta. Okay. So so we call this objective a loss. Okay. So for regression, you can simply use this as a loss. We call this a MSE loss. And for classification, you should use a very special loss. We call it cross entropy loss. This is related to the entropy that you learned in your decision tree. So very similar. So P times log P. Okay. So why it's using this? Because it's good. Okay. Why it's good? I don't know. Okay. So there's a lot of explanation. You trust it or not, but this is performs very well. Okay. So I just want you to remember this key term, that no matter what type of loss you are using, eventually it will give you a scalar. Okay, no matter how complicated your model is, finally at the end, your objective should be a single number. Okay, so here you can see MSE loss, no matter how complicated your Y is, maybe it's a vector or it's a matrix. Say for example, you want to generate an image. It's a matrix. Okay, so your final loss should be always a scalar, because only when it's scalar you can minimize it. Okay, so all those loss are definitely a scalar. Okay, so how do you find the loss? How do you define the loss? This is based on the task. Okay, different task has different loss. In general, designing a loss is extremely challenging. Okay, so basically, for example, here regression, everyone think this is good, then you just use the one. Classification, everyone use this one, you just use this one. Okay, and for your specific task, usually there will be some loss that developed by the people. Okay, you just use that one. Okay, designing a new loss is already a very good paper. Okay, so this is very difficult actually, in many cases. So I just suggest that you, based on the practical experience, okay, people has already developed a lot of loss for different tasks. You just use them. Okay. The cross entropy, so this one is particularly used for classification. As long as you're using classification, this one is particularly good. Okay, so I skip those things. So, okay, so then you can see that what we are doing, we just want to do a minimization problem. We want to minimize the loss by changing the parameter in the neural network. Okay, parameters include weight and bias, and there are millions and billions parameters in the neural network, but it's just parameters, right? So what we can do, still, if you still remember, we have learned the gradient descent, right? So gradient descent says that if we want to minimize it, very simple, we just calculate the gradient of the objective, and then we update by the negative gradient. So given a theta, we calculate the gradient at the theta, and then we use some learning rate, we can update the theta. We just keep doing this, we can find a good theta. Okay, gradient descent. We learned this, right? Okay, so then that's very straightforward. Okay, let's make it more concrete. Okay, let's make it more. Let's say we have a gradient descent. We have a neural network. So eventually we calculate L. L is a scalar. Okay, so here we have W1, we have W2, we have W3, we have W4. Okay, and we have B1, B2, B3, B4. Okay, so when we talk about partial L, partial theta, what are we talking about? So L, scalar. Okay, theta is actually very complicated. It is theta include W1, W2, W3, W4, B1, B2, B3, B4. Okay, so first thing, what is the dimension of partial L, partial theta? The dimension is the same as the summation of all those parameters, right? Okay, so maybe I ask you another question. So if I have a function f, input is theta and output is a scalar c. I ask you partial, this one is dimension d. Okay, so partial f, partial theta, what is the dimension? It's d dimension, right? So basically, partial f, partial theta, if f is a scalar, then the dimension is equal to the dimension of theta. Right? These two dimensions should be the same. If f gives you a scalar, right? Right. Okay. So this basic calculus, right? So here you can see that if I'm calculating partial L, partial theta, I'm actually doing is I want to calculate partial L, partial W1, partial L, partial W2, all the way to partial L, partial B1, partial L, partial B4. Okay. So as long as I have those one, so here I just use one equation, theta equals theta minus this one. So what I'm actually doing is W1 equals W1 minus partial L partial W1 TK. B4 equals B4 minus TK partial L partial B4. Okay, so you are updating each of the parameters separately. As long as you know the partial L, partial theta is a very generalized concept. It contains all those partial derivative. Okay. So I think I don't need to explain why the gradient descent works. Okay, so gradient descent basically it can give you the minimum location. Okay, so you can find a way to the minimum. Okay, so this slide gives you the idea why the gradient descent look like that. So it's actually you can think of it as so you do a Taylor expansion at x location. So for y is near x. So if y is near x, so fy is fx times the gradient of fx and y minus x, and this is Taylor expansion, second order Taylor expansion, right? So this equation holds. And how do we find the smallest y? We take the derivative of this part, right? So we take the derivative of this part, and then we make it 0, and then you get this one. You get y should be y at x minus t derivative. This gives you the interpretation of why the gradient descent always goes to a lower result. Okay, so here we have a t. This t, we call it a step size, or we call it learning rate. Or a step size. So both okay. Okay, so here you can see that if the step size is too large, so you can see that it start to it's actually does not converge. If the step size is too small, it cannot go to the final result. I think these are all easy to understand, right? So basically, you need to choose a proper step size. Okay, so you have the step size, and suppose you can calculate the gradient. And what you can do is very straightforward, right? So you just calculate, update each of the parameters separately. Okay. So there's one more thing. I think I don't have time. So we are talking about gradient descent. So in the neural network, actually, we are not using gradient descent. We are using stochastic gradient descent. So where does the stochastic come from? So it's mainly because if we need to look back the loss. So the loss has a very key issue of here. You can see here, it means that you have to sum for all the data. Okay, so when you calculate the gradient, it's basically you need to calculate the gradient for each of the data, and then you sum them together, take the average. This is very time consuming. Okay, okay, so dimension, I talk about this, but this one is very consuming. So basically what you need to do is that you need to look at all the data sets once so that you can run one iteration. Right, so you have to go through all the data to calculate one by one. Then finally you can find the final the loss. Then you can update once. So in this case, one epoch is one iteration, and it's so it's one update. Okay, so this one is actually not very efficient. So people come up with a new idea that you don't do for all the data sets. For example, you have all the data set n. What you can do is that you can partition it into different batch. So every time you only calculate a batch of the data, and you take the gradient for this batch of the data. Okay, so in that case, so for example, you have b number of batch for this data. Then in this case, in one epoch, you run b iterations. You update the parameter b times. But every time, the gradient is only calculated by part of the data. Okay, so this is called batched batch size, batch gradient descent, or in generalized, we just call it stochastic gradient descent. The stochastic is because the gradient is stochastic. Okay, you don't evaluate the actual gradient. You only use part of the data to evaluate the gradient. Okay. So technically, which gradient is better? So I think it's easy to understand. It's very straightforward. The using all the data, you get a good gradient, right? So technically, you should have something like this, right? So gradient descent give you a very good convergence, but the stochastic gradient there might be some fluctuation. Okay, but there are theoretical proof that both gradient and subgradient, gradient descent and stochastic gradient descent, they can give you the final results. Okay, so they have some proof on this. But there is a observation. So in neural network, SGD performs better than GD. Okay, so this is very counterintuitive. So if you are using the SGD and GD, you run the same number of epoch, you'll find that SGD will give you the better result. And even though you run more time for using the gradient descent, SGD still gives you the better result. So better result means that your neural network is trained better. It performs better on the testing data set. Okay, so this is very counterintuitive. Okay, why? Do you know why? Because in the neural network, stochasticity is a good thing. So in this case, you can see that stochasticity is not a good thing. But what we are facing is something that is something like this. It's a nonlinear scenario. Okay, the stochasticity actually helps you to jump from local minima. Okay, so adding some randomness is actually better for training in this case. So stochasticity helps to overcome local minima. Or I shouldn't say overcome, escape. Okay. This is one reason, and actually there are more reasons. It's too difficult to understand. Maybe I don't say. So basically, so this is very interesting observation. Okay. In the traditional optimization, SGD is definitely better. But in neural network, in this highly nonlinear situation, so for example, in the gradient descent, so here, if so, for example, you're stuck here, and if you're calculating the gradient, it's always 0. But if you're calculating SGD, stochastic gradient, maybe it's something not 0, then you can jump to here. Okay, so this kind of randomness actually helps the model. So there are professors particularly working on why the SGD is perform well and how it can be used. If you're interested, you can look at this. So there's another statement. Maybe it's difficult to understand. So SGD helps to improve the robustness of the model. Okay. It's mainly because the model get used to the noise, get used to this randomness, and it actually performs better in the testing dataset because testing dataset usually it contains some noise. Okay. So they have some mathematical proof on this, but here is just some description to help you to understand. So in general, no one will use GD in the neural network. You definitely will use the SGD, and you will choose a batch size. So here we have a terminology, batch size. Batch size means how many number of data that you use to calculate the gradient. Okay, so large batch size, more smooth gradient. Low batch size, small batch size, basically the gradient will be more random. Okay. Okay, so here you can see that we talk about gradient descent, we talk about SGD. So now you know that as long as we can calculate the gradient, we can update the parameter. We can update the weight and the bias, and then we train the model. So we just keep doing this, we train the model. So the only thing that we don't know is how we can calculate partial L, partial theta. Okay, so this is the last part, gradient computation. But this part is actually not very useful because in PyTorch, those modern packages, you don't do this part yourself. The package will calculate the gradient directly for you. Okay, so this whole part is automated. There is a very famous paper, I forgot the name, but this technology called auto differentiation. Okay, so for PyTorch is based on this technology. PyTorch, TensorFlow, they are all based on this technology. So they can do automatical differentiation. So basically it says that no matter what type of neural network structure you designed, as long as you use PyTorch, it can calculate the calculate the derivative for you. You don't need to do anything. Let me see if I can search on this paper. Auto diff. Yeah, something like this. So auto differentiation. Okay, so basically there's a structure design. So this has nothing to do with math. So it's basically systematical design to make sure that this implementation can systematically take the derivative for you. Okay, so if I'm interested, next week I think if I have some time, I can talk about this. So I think you know another name called backpropagation. So basically, it's using the backpropagation, but this is no longer important, I think. So in the modern programming languages, no one will do the gradient descent yourself. No one will do the gradient calculation yourself. So it's just simple, it's just one line code. You can calculate all the gradients. Okay. So next week, if I have time, I can do this. So one thing I want to mention that for the so the PyTorch is different from scikit-learn. Scikit-learn is that they implement one package, one method for you, another method for you. PyTorch is actually they give you a lot of building block. Okay, so the building block that involves, like I just mentioned. So here you can see that it has multiple. Wait a second. So here you can see that it has torch dot something. Okay, for example, torch dot nn, that basically is a lot of layers. It's a building block that you may use, and torch dot n dot function nulls that include a lot of functions that does not contain the parameters. Okay, and torch dot optim, this one, this basically this contains gradient descent, most of the gradient descent method. Okay, so another one, auto differentiation. I think there's also a package for differentiation. So basically, this one, autograd. So basically, automatical gradient computation. So basically, you can see that you have different building block in PyTorch. And later, if you want to develop your deep learning method, you need to combine. For example, which layer you're going to use, which gradient descent you're going to use, and then you just combine them together. You build your own model. Okay, so this is different from scikit-learn because scikit-learn decision tree is just decision tree. Okay, here it's a lot of building block that you want to. It's like a Lego's part, and you want to build your Lego by yourself. Okay. Okay, so one thing is that in some of your research, maybe you don't want to use this whole package. You just want to use the auto differentiation. There are some other packages I will highly recommend you to take a look. I'm not sure you heard about this, JAX. Yes? No? JAX? JAX is developed by Google. So it's basically a framework that can help you to calculate the gradient. Okay, So for example, later, if you have some research question that you need to calculate the gradient, but you don't want to do it by yourself, you just use this framework and it can automatically calculate the gradient for you. And this is built on NumPy. Okay, so here you can see that you just use NumPy language. You just use NumPy array, and then it can automatically derive the gradient for you. Okay, so this Jack's grade. Okay, so you can see that this is part of the PyTorch. PyTorch is multiple function, and this one is only gradient. Okay, so if you're interested, you can take a look of there's a lot of package like this. So part of the so I think it will take time if you really want to do the deep learning research. You have to take a long time to read the PyTorch document because it's super long. Okay, if you're interested, then I would suggest that you just start writing something. Okay. Okay, so that's it for today. Next week we'll have a test. Okay, the content is basically everything that I taught till today. Okay, so lecture 4 lectures, right? 4 lectures content and close book. So no worries, it does not count too much score, so it won't be a very difficult issue. It's just, yeah, usually the PhD subject we won't fail anyone as long as you submit all your homework and the report. Okay, so the test is just help you to get a flavor of what the question will look like, and also help us to get find who will get A+. Okay, if you don't want A+, the test is not very useful. Okay, so that's it. If you have any question, let me know. Okay.